So this is the last section of the volume unit, and we're going to go over Cavaliers Principal today and the volume as it relates to density. So Cavaliers Principal says if two solids are between parallel planes and all cross sections at equal distances from the base have equal areas, the solids have equal volumes. So let's talk about what that means. So we have a cone here and we have a pyramid. So if the area here of that base and this base were the same, and the heights were the same, then we could say the volumes of these two shapes are the same. Even if we go up the same distance, so let's say this whole thing was 12 inches and we moved up to, let's say, 6 inches. If we move 6 inches up, then and this area right here and this area right here are the same again, then we could still say that the volumes are the same. Same way if we moved up 10 inches. Notice that these are parallel lines and they have to do with parallel planes. And that's what this says. It says this cone and this pyramid have the same height and the cross sections have the same area, so they have equal volumes. So an example of that here is if we look at this base, it's 6 by 4. That would be 24. And this prism over here is 5 inches tall. This one is 12 by 2. So it also has the same base area. So that would also be 24, and the height of this would be 5 inches. So the volumes of these two are base times height. So we would see that both of these would be 24 times 5, and thus they would have the same volume. So the volumes are the same because the base areas are the same and the heights are the same. And we're using the same equation, base times height. So on this next one, it's just, again, another example of Cavaliers Principal. So if we talk about these two cylinders here, so if we were to stack all these right on top of each other, we would have a base that's a circle, and the height. In here, this is the same number of CDs, so it still is the same base because the CDs would be the same size and the same height. So the fact that this is slanted does not change the volume because the height would still be the same. So here I would like you guys to go ahead and compute the volume of the cylinder, both cylinder A and cylinder B. When you're doing this problem, remember, we don't use diameter to find the volume of a cylinder. We use the radius. So the very first thing we'll have to do here is find the radius, which means we're going to divide the 5 by 2. So our radius is going to be 2.5. Our formula here is going to be base times height, which is pi r squared h. When we do that, we're going to square the 2.5 and multiply that times 14, and we're going to give our answer in terms of pi here. So this is going to be 87.5 pi meters cubed. Over here again, our radius is going to be 2.5 and our height is going to be 14. So essentially, it's the same exact equation, and you should be able to see here that obviously the volumes are the same because the radius is the same and the height is the same. And yes, that should be centimeters there because that was centimeters up there, y'all. Sorry about that. All right, so then this next one says example 2. This time we're going to use Cavaliers Principal to determine again how do the volumes compare here. So we have a cone with a base area of 24 inches squared, which means that circle has an area of 24 inches squared and a height of 10 inches. And then we have a pyramid with a base area of 24 inches squared. And a height of 10 inches. So our formulas here are both 1/3 base times height. Just so happens that we are given the base here, so we're just going to multiply the 24 times the 10 and divide it by 3. That's 80 inches cubed. Well, when we look at the volume over here, it's essentially the same because our numbers are the same. So that means it's going to be 80 inches cubed as well. Now here's the key, guys. When you guys take your test on this, you're going to have to describe how do the volumes compare and why. So that's really important that you guys can be able to write that out. So if you don't know what to write, then you need to pause the video right now and you need to write this down so that you are capable of writing it on the test. So the volumes are the same because, why? The base areas are the same and the heights are the same. And we're using the same equation. We're using 1/3 base times height. So this is essential that we're using the same equation. On the prior problem, it was just base times height. These are both 1/3 base times height, so that's really important as well. All right, so the next concept we're going over has to do with density. Now, Density has to, when I say something's dense, it's closely compacted. So if I'm talking about a marshmallow and a rock, obviously a rock is more closely compacted than a marshmallow. So we could say that the density of the rock is higher than the density of the marshmallow. The formula for density is equal to mass over volume. And the way I remember this is the DMV, as in the Department of Motor Vehicles, which I know all of y'all are interested in because you're trying to get your driver's license or already have it. So then this is what you have to remember. We will not give you this formula. Density equals mass over volume. And most of y'all are taking chemistry and have seen this before. So again, density is equal to mass over volume. We can solve for this, any of these variables. So when we're solving for mass, it's density times volume. When we're solving for density, it's mass divided by volume. When we're solving for volume, it's mass divided by density. And again, you can just do D equals M over V and solve for the missing part. So if we look here, it says, consider the two boxes below. Each box has the same volume. Which box is considered to have a greater density? And if you look at block 2, obviously the molecules in block 2 are closer together than the molecules in block, the molecules in block 1 are closer together than the molecules in block 2. So obviously I'm expecting block 1 to have a higher density than block 2. But let's go ahead and compute this using our formula. Density equals mass divided by volume. So on the first one, we're going to go 79.4 grams divided by 29.8 centimeters cubed. So our answer here is 2.66 grams per centimeters cubed. Same thing over here with block 2. We're going to divide 25.4 grams by 29.8 centimeters cubed. This time we get 0.85 grams per centimeters cubed. All right, so block 1 obviously has a greater density. All right, so now let's talk about this one, example 5. It says a sphere gas tank has the dimensions shown when filled with gas to provide 117,500 BTUs of energy. To the nearest 10 BTU, how much energy does 1 cubic foot of the gas yield? Show your work. Okay, so we got to do a couple things here. First of all, I am looking at this question trying to figure out, what is it even asking me for? Is it asking me for volume? Is it asking me for mass? Is it asking me for density? So I want you guys to notice something here. It says how much energy, that's my BTUs, per cubic foot. The fact that there's two different measures there tells me this is a density problem. So that's really important, first of all. And BTUs, really also important, is BTUs has to do with mass. And y'all need to remember this because the question on the test has to do with BTUs, okay? So, then what we got to find is the volume. Well, the biggest thing I notice here immediately is that this is a diameter, so we have to find the radius. So to find the volume of the sphere, we need the radius, and so the radius is obviously half the diameter, so that's going to be 3. We're going to plug that into our formula for the volume of a sphere. That's 4/3 pi r cubed. So we're going to cube the 3, multiply it by 4, divided by 3, and then this time we are going to multiply it by pi. So go ahead and do that. What you should have gotten is 113.10, and we rounded this up to the 10. Now we want to go ahead and put that volume and our mass into the equation for density. So the density is equal to 117,500 divided by 113.1. Again, you should see that our density was 1,038.9. Notice here again it says to round it to the nearest 10 BTUs. So we are going to round that to 1040 BTUs per feet cubed. So the next two problems, guys, we're going to still use our formula, density equals mass over volume, but we're solving for different things now. We're not solving for density on this problem. We're given the density and the volume, and we're trying to find the mass. So again, we're just going to put those into this formula, density equals mass over volume. Given the volume, that's going to go on the bottom. We're given the density this time, and so it's going to go on the left. Recall that the way we get rid of something that's in a denominator is to multiply both sides by what's there. So this is exactly what we're going to do here to get rid of that 600 on the bottom. So that's how we're going to solve for our mass. So that is 7,998 grams. So our next problem says, given a mass of 1,500 grams and a density of 0.00222 grams per millimeter cubed, what is the volume? So once again, we're going to use our same formula. The difference is this time we're populating different things. So this time we are given our mass and we need to solve our volume. Now, if you should recall, when we were doing trig, our sine, cosine, and tangent, that we told you guys that you could swap these two things. Hopefully y'all remember that. And so we're going to divide that 1,500, maybe if my mouse works, by the 0.0222. So go ahead and do that. And notice again that our grams are going to cancel out here as well. So we're going to be left with millimeters cubed. So when you do that, you should get 675,675.68 millimeters cubed.